So I'll start off with a brief summary of what we ended up talking about in the last lecture. So we wanted to extend the idea of ESS to finite populations, and we saw that it is necessary to change our idea of ESS when we go to finite populations, because in finite populations any strategy can get fixed with a certain probability, and it is not enough to ask whether the fitness of a mutant is smaller than the fitness of the remaining wild type population. That leads to a condition which is neither necessary nor sufficient in order to determine ESS in finite populations. And we saw that from this example, where we asked the question, when can a population of D-type players avoid being invaded by a single C mutant? So C and D are two types which are playing this game with each other. And so F1 is the fitness of a single C mutant that appears in the population, and G1 is the fitness of the remaining n-1 wild types, D wild types that were present in the population. And this condition, that the fitness of a single C-type mutant must be less than the fitness of the remaining n-1 D types in the population, leads to a condition B less than C, which is neither necessary, which is different from the condition that you for ESS that you get by looking at the payoff matrix, which requires that for D to be an ESS, D has to be either larger than B, or if D equal to B, then C has to be larger than A. So the infinite population result for D to be an ESS is neither necessary nor sufficient when you go to finite populations, right? And so it became clear that we need to introduce the notion of fixation probability, and we have to ask the question whether not just whether the fitness of a single mutant is larger than the fitness of the remaining n-1 wild types, but also whether the mutant can take over the population of wild types with a probability which is larger than what is expected by chance, which is the neutral fixation probability. So for D to resist invasion by C, the fixation probability, or rather the invasion probability of C, must be larger than 1 by n, which is the neutral fixation probability. Okay, and so that requires us to calculate this invasion probability or fixation probability, and we could do that by using the machinery that I developed, that I discussed in the first lecture. All you need to do is to consider a Moran process of evolution, where at every step one individual is selected for reproduction and another for death, and the individual selected for reproduction is done so with a probability proportional to its fitness, and the one that is selected for death is chosen at random. So you can calculate the transition probabilities to go from a state where the number of C's change by 1, increase by 1, and the number of C's decrease by 1. The ratio of the transition probabilities will give you this quantity gamma I, and the fixation probability can be calculated in terms of this quantity. But the main technical challenge lies in calculating this complicated sum and product thing, but it can be done in certain approximations, which we talked about, which is the weak selection approximation, where if I define my fitness in terms of this parameter W, where W essentially determines the extent to which the payoffs arising from interaction contribute to the fitness. So in the weak selection limit, what this means is I'm saying that the fitness of an individual is weakly dependent on the interactions that that takes place with other members of the population. And in that weak selection limit, I can get an expression for the condition for which the invasion probability of C is larger than the neutral fixation probability. That turns out to be translate to a condition on the population size, and for fixed values of the payoff matrix elements A, B, C, D, the condition leads to a condition that the population size has to be larger than the critical threshold. But when you have a fixed population size, this condition reduces to a condition on the payoff matrix elements, and in the limit of large population sizes, we found out that we could establish a nice correspondence between the condition that we get and the infinite population result. Because in the infinite population case, we could solve the replicator equation and obtain the mixed state equilibrium frequency. And it so happens that if the mixed state equilibrium frequency happens to be smaller than 1/3, then that tells us that in the corresponding finite population model, the fixation probability of a C mutant would be larger than what is expected by chance. So by going back and forth between the infinite population replicator dynamics and the finite population Moran process of evolution, you can predict that when the fixation probability of a mutant is going to be larger than what is expected by chance. And this led to this kind of phase diagram where the different regions demarcate the regions for which the fixation probability of the two different types will be larger than what is expected by chance. Okay, so now let's introduce another concept called risk dominance. So suppose you have a situation in which both C and D are a strict Nash equilibrium, or in other words, both are an ESS, right? So then if you want to ask the question, which one is more likely to invade the other? So if you start with a population of primarily D players, introduce a C mutant, and ask after interactions between these two whether the C mutant can take over D, and alternatively you start with a population of C players, introduce a D mutant, ask whether the D mutant can take over the entire population, right? So in the case of infinite population dynamics, we know that if both are an ESS or a strict Nash, then neither can take over the other. Right? But for finite population, that is no longer true, and so we can calculate the ratio of the fixation probabilities and determine the condition under which the fixation probability of D is smaller than that of C. And this can be done again in the weak selection limit. So all you have to do is to calculate the product. So you plug in the expressions for GI and FI that we obtained earlier into this equation. This is a product. You multiply the different terms that appear, keep only the terms which are linear in W, which is a weak selection, which is selection parameter, and you end up. It's a bit of an algebra, but a fairly straightforward calculation, and you end up with this ratio. So this ratio tells you that where x is this quantity. So if x is larger than 0, then the fixation probability of D will become smaller than the fixation probability of C. And then we can say that C is more likely to take over a population of D wild types than D is likely to take over a population of C wild types, right? And so what happens when x is larger than 0? We end up in the large n limit. So if you look at this, and so in the large n limit, this term dominates compared to this term. So if you put this to be larger than 0, you end up with this condition. So what does this condition tell us again? So A plus B is the payoff the total payoff to A player when it interacts, to a total payoff to a C player when it interacts with C and when it interacts with D, right. So, this is the condition tells us that the total payoff to the C player must be larger than the total payoff to the D player, which is C plus D, in order for the fixation probability of C to be larger than the fixation probability of D. And you can again establish a correspondence with the infinite population model. This condition essentially means that if you calculate the unstable mixed state equilibrium frequency, it should be less than half. Okay, you can see from this that it leads to this condition that x star is less than half. So what this means is, if you have a finite infinite population replicator model, you solve the model, find out the equilibrium mixed state equilibrium frequency, and the value of the mixed state equilibrium frequency will give you insights into the fixation probability of a mutant, either C or D, in the corresponding finite population model. Okay. And so this is a final diagram which contains both conditions for the fixation probability and conditions for risk dominance. So risk dominance condition, so C is a risk dominant strategy if the fixation probability of C is larger than that of D. D is risk dominant if this is valid. And so you can see that if the mixed state equilibrium frequency lies somewhere in this regime, then C would be risk dominant and the total payoff to C would be larger than the total payoff to D. Okay, so now we have all the ingredients that are needed to modify our definition for ESS in finite populations. So one thing should be clear by now, that the ESS condition for finite populations depend on the population size, right? And so let's establish a further contrast between the infinite population case and the finite population case. So in the infinite population case, suppose you have this situation, A larger than C and B larger than D. That means that C is a strict Nash equilibrium as well as an ESS, but D is not. So in this case, the infinite population intuition tells us that C cannot be invaded by a D mutant. So in this case, you have both C and D to be an ESS, and it tells you that the infinite population neither can invade the other. But if you go to finite populations, we have seen that we need to look at two conditions in order to determine which strategy is an ESS. One is whether the fitness of a single mutant is smaller than the fitness of the n-1 wild types, and the other is whether the fixation probability or the invasion probability of a mutant is larger than what is expected by chance. So for C to be an ESS in a finite population of size n, we must have the fitness of a single D mutant, which is given by G n-1. Remember that n-1 refers to the number of C players in the population. So G n-1 is the fitness of a single G mutant in a population with n-1 C players, which has to be smaller than the fitness of n-1 C players, and the fixation probability of C must be larger than 1 by n, and fixation probability of D must be smaller than 1 by n for C to be an ESS. So the fixation probability of every other strategy has to be smaller than the neutral fixation probability, and the fixation probability of C must be larger than the neutral fixation probability. And similarly, one can write down a condition for ESS n. Okay, so now let's look at some example, and we ask the question, when is D an ESS? And we saw that it leads to this condition. We have already seen this calculation before, but we also need to impose this additional condition that the fixation probability of C must be smaller than 1 by n, which leads to the condition on the mixed state equilibrium frequency in the corresponding infinite population replicator model. Now, if you plug in the values of n in either of this, so for n equal to 2, f1 smaller than g1 leads to the condition b is less than c, and even this condition, if you put n equal to 2 in this inequality, you get the condition that rho c, for rho c to be less than half, because n equal to 2, b must be smaller than c. Now, you can see that this is different from the condition for ESS in an infinite population case, where for D to be an ESS, you needed D to be larger than B. So, that condition is neither sufficient nor necessary. Now, let us look at two examples to see how the ESS condition can change with population size. So, if you have this kind of payoff matrix, so this is a question that I am going to ask you to make sure that all of you have not fallen asleep. So, if you look at this this payoff matrix, can you tell me which is an ESS in this case?
C.
Yeah, CC, you can just say C is an ESS, but what about D? So what is an ESS condition in the infinite population limit mean? Right? I look at the payoff to D when it interacts with another D, and then I ask if one of those D's change to C, does it end up with a higher payoff, right? So payoff to D when it interacts with another D is 1, but when one of the D changes to C, the C will get a payoff equal to 0, which is lower than the earlier payoff, right? So in this case, both C and D are ESS strategies, right, which says that neither can be invaded by the other, right? But if you ask the condition, if you ask what is the condition for infinite population for D to be an ESS, we find that the first condition leads to this, which is automatically satisfied, and the second condition, which is rho c has to be smaller than the neutral fixation probability, leads to a limit on the population size. So D is an ESS only for population sizes which are smaller than 53. Beyond that population size, we cannot say that D is an ESS, even though the infinite population picture implies that D is an ESS. Okay. So I hope this convinces you that in the finite population scenario, the concept of ESS has to be radically modified, and the concept of ESS depends on population size. So whether a strategy is an ESS or not will depend on the size of the population. So here's another example. So can you say which one is an ESS here? By looking at the payoff matrix, the ESS in the infinite population model. D is the only ESS, right? C is not an ESS because if two players were playing C, they would get a payoff equal to 1, and if one of them changed their strategy unilaterally to D, it would end up getting a higher payoff, right? So D is the only ESS here. But in the finite population scenario, for D to be an ESS, we find that the first condition leads to the condition that the population size has to be larger than n, larger than 15, and the second condition, which has to be satisfied in the finite population scenario, which is the fixation probability of C must be smaller than 1 by n, leads to a more stringent condition, which says that n has to be larger than 17. So even though the infinite population intuition tells us that D is an ESS. For finite populations, we can say that D is an ESS only for population sizes which are larger than a certain threshold, which is 17 in this case. Okay. So, any questions? Okay. Okay. So, here's another model. Again, I'm not going to go through the calculations in detail, but I just wanted to give you a sense that the manner in which we update the population can be changed, right? So, in the Moran process example, what we were doing is we were calculating the fitness of both C's and D's in the population in a way that accounts for the fact that the fitness is frequency dependent. And then we were asking what is the likelihood of picking C for reproduction with a probability proportional to fitness, and what is the likelihood of picking, say, D for death by chance, right, at random. So, an alternative to that mode of population update is given here. It is called the payoff comparison method. So, instead of picking individuals for reproduction with probability proportional to fitness, what we can do is compare the fitness of the individual that we have picked for reproduction with the fitness of the other type present in the population. And if then we can decide based on this function whether the one that we have picked for reproduction should be selected to replace the one that has been picked for death. So, why is this interesting? Why is this update mechanism interesting? First of all, it allows us to compare the fitness of the two types, right? So, does this seem familiar, this function seem familiar to anyone, especially the physics students? Are there any physics students here? Yeah, it's a Fermi distribution, right? So, this Fermi distribution, so this tells us that if W equal to, suppose Fd equal to Fc, right? So, then what will it happen? How do I decide which one to pick? Well, then I am going to pick at random. So, I am going to select C with a probability of half and select D with a probability of half. But if Fd is not equal to Fc, suppose Fd is larger than Fc, and suppose W is very large. So, for physicists, W is the analog of beta, the inverse temperature. So, even though here you can think of it as a selection coefficient. So, if in the limit W tending to infinity, if Fd is larger than Fc, then C will be replaced by D with a probability equal to 1. Okay? And in the other situation, if Fd is smaller than Fc, then C is retained with a probability equal to 1. So, this gives us a mechanism of comparing payoffs and deciding which strategy to pick depending on whether it has a higher payoff or not. Okay? And so, in the limit of large W, we are always going to pick the strategy with a higher payoff, but for finite W, we are going to pick the strategy with a higher payoff with a certain probability which is determined by this function. And so, if the other usefulness of using this function comes from the fact that analytical solutions are possible not just for the weak selection strength case, but for all selection strengths. And you can calculate the transition probabilities here. So, this is a probability of choosing one of the two for reproduction, and this is a probability that you do indeed select that for reproduction, and this is a probability of choosing the D type for death, and so on. So, you can take the ratio of these two transition probabilities, and it leads to a fairly simple expression which can be calculated exactly. So in the limit of, so when you are using this update rule based on a pairwise comparison of the fitness of the two types that are present in the population, you can calculate exactly the condition for risk dominance again, and it leads to the same condition. But for fixation probability, you can do the calculation exactly only in a certain limit, which is this case. So it becomes difficult to calculate this complicated product sum factor, but it is possible to do so in the limit where this condition is satisfied. So what does this condition mean? So if you look at the payoff matrix, what does this tell you? So it tells you that suppose both of the players were playing C, they would each get a payoff equal to A, right? And then unilaterally one of them changed his strategy to D, and what is the difference in payoff that results? The difference in payoff would be A minus C, right? Because now that original C player who is continuing to play C would get C when it was previously getting A. So the difference in payoff would be A minus C. Now suppose you have two players who were playing D, and one of them decided to unilaterally switch his strategy from D to C. So when he does that, he gets a payoff equal to small b, and so the difference in payoff would be B minus D. And so this condition means that the payoff difference is the same regardless of which strategy one of the players unilaterally switch from. And if this condition is satisfied, then it is possible to calculate the fixation probability of C and D exactly. And if you look at the expression, you can see by comparing it with the fixation probability for a case where the fitness was of one of the mutant was R and the fitness of the wild type was 1, the fixation probability gives an exact correspondence when you put R equal to e to the power WV. So why is this result worth sort of pointing out? It's because this is the case that was obtained when we were considering a strategic interaction, a game, right, where we had frequency dependent fitness. But this is a result that was obtained when the fitness was constant. So in this, for this particular case, the fixation probability turns out to give an expression which can be mapped on to a problem with which looks at evolution with constant fitness. Okay. So this was one of the motivations for pointing out this new method of strategy update or population update, which is distinct from the Moran process method. Okay. So any questions? Yes, yeah. So that's an important point. So we are still working with a well-mixed population. So anyone can interact with anybody else in the population with equal likelihood. Okay. So now let's go to a game where and look at the condition under which one of the two strategies that you saw that was discussed in Shagor's lecture yesterday, whether they can invade in finite populations, in a finite population situation. Now, this is a game between two strategies. One is called tit for tat and another is called all D. So if you remember, tit for tat is a strategy which starts off by playing cooperate, but if the opponent defects, it shifts to defect. So the philosophy is, if you are nice to me, I will be nice to you and cooperate with you, but as soon as you are mean, I am going to be equally mean and start defecting. But if the opponent reverts back to cooperation, then tit for tat will again revert back to cooperation. Okay. So this is a game between TFT and ALDI. ALDI is a strategy which is purely selfish, which is defecting all the time, right? And so in the infinite population limit, one can write down a payoff matrix between a tit for tat player and an ALDI player, right? So which depends on the average number of rounds, right? So if two tit for tat players are playing with one another for, say, an average of m rounds, what would be the payoff or at the end of m such interactions to each of them, right? That is a question that we are asking. So both of them would start off by cooperating, and both would continue to cooperate for m rounds, right? So so at each round, each of them will get a payoff equal to small a, and so for m rounds, they are going to get a payoff equal to m times a. Okay. So when tit for tat is interacting with ALDI, what is the payoff that TFT will get at the end of an average of m rounds, right? So in the first round, tit for tat will start off by cooperating with ALDI, and it will get a payoff equal to small b. But for all subsequent rounds, because ALDI had defected in the first round, tit for tat would defect, right? So you would have this situation where so TFT starts off by cooperating and then plays defect all the time, and ALDI of course starts off by defecting, which is why TFT plays defect in all subsequent rounds, because ALDI keeps defecting. Okay, so this is a situation that we have, and you can calculate the payoff here. Similarly, the payoff to ALDI would be the first time they interact, ALDI can exploit the cooperative nature of tit for tat and get a payoff equal to small c, and but for all the remaining m minus 1 rounds, it will get a payoff equal to m minus 1 into d, and so on. So we know that in the finite population, infinite population limit, for TFT can avoid being invaded by ALDI if the total payoff to TFT when it interacts with another TFT is larger than the payoff to ALDI when it interacts with ALDI. So if this is larger than this, then TFT will be a strict Nash or an ESS, and this condition amounts to a condition on the average number of rounds, which looks like this. And you may recall that in Shagor's lecture yesterday, he talked about this concept of the shadow of the future, in the sense that there's no guarantee that the game will continue for m rounds. So it's we can only talk of the game being continued for the next round with a certain probability delta, and in that case the average number of rounds happens to be 1 by 1 minus delta. So this was what Shagor had done yesterday in his lecture. Okay, so the infinite population scenario then tells us that TFT and ALDI are both ESS if this condition is satisfied in the infinite population limit. So TFT cannot invade ALDI, ALDI cannot invade TFT, right? But let's look at the finite population scenario. So here, so we can evaluate those two conditions. The fitness of a single TFT mutant has to be larger than the fitness of n minus 1 ALDI players for TFT to be able to invade, and the fixation probability of TFT has to be larger than 1 by n, right? So you can plug in the you can calculate the fixation probability of TFT in the same way by plugging in the expression here. Just replace C by TFT and D by ALDI, and replace A and B and C and D by the corresponding payoff matrix elements that you see here. So A will be replaced by MA, B will be replaced by this, and so on. And so you can calculate it and obtain a condition which translates to a condition on the average number of rounds for a fixed population size. So if n equal to 2, this means that the average number of rounds must be infinity, right? So TFT can never invade all D if the population size is 2. And that makes sense intuitively, obviously. So if you have n equal to 2 means that there are just 2 players. One of them is a TFT, another is a all D. So TFT will start off by cooperating and be exploited by all D, so it will get a lower payoff in the first round, but for all subsequent rounds their payoffs will be the same. But since the TFT got a lower payoff in the first round, its payoff will always be smaller than that of all D, right? So for n equal to 2, obviously TFT can never invade, right? But for n equal to 3 and n equal to 4 and other values of finite values of n, it just puts a constraint on the average number of rounds that you have to play for TFT to be able to invade the population of all D players. Now, if you fix the average number of rounds, this translates to a condition on the population size. So this says that TFT will be able to invade a population of all D players if the population size is above a certain threshold. Now keep in mind that, so what do we see from here? We see that although this is not visible because the numbers here start from very large population sizes, but as you go to population sizes, rho TFT into n becomes smaller than 1. Okay? So that means rho TFT becomes smaller than 1 by n, which is the neutral fixation probability. So then for population sizes for which n rho TFT becomes smaller than 1, TFT will not be able to invade, and for population sizes which are larger than a certain threshold upper bound here, then TFT will not be able to invade. But this condition just gives you just one bound, right, which is the lower bound. Why do you not get the upper bound? Any guesses? This is a difficult question. So the reason is that this condition was obtained in the weak selection limit. And so in the weak selection limit, what we have, so this is an example where the selection is fairly weak, so you see that you don't have this upper bound. So n rho TFT becomes, remains larger than 1 even for very large population sizes. So for a fixed number of rounds, the lower bound is 3. So for a population size larger than 3, TFT will be able to invade in the weak selection limit. But for population sizes which are larger than a certain upper bound, which is not evident from this relation, but is evident from these simulations, in the strong selection or moderate selection regime, there exists an upper bound on the population size. So why is this? Why do we have an upper bound? Can we intuitively understand the existence of an upper bound on the population size beyond which TFT cannot invade? So let's think of what's happening in the game. You have a population, you have TFT players and all D players, right? So TFT players start off with just one TFT player in a population of all D, and then gradually try to increase their numbers. Now, when the number of TFT players is small, they interact with each other, and when they interact with each other, they act as cooperators, right? TFT cooperates with other TFT players, and when they interact with each other, so they can get the benefit of mutual cooperation. Because keep in mind that the benefit of mutual cooperation is larger than the benefit of mutual defection, right? So as long as TFTs are interacting within themselves, they are able to increase their payoff because they get the benefit of mutual cooperation. But when they are interacting with other ALDI players, they are being exploited, and that reduces their payoff, right? And so this happens, so TFTs can gain the benefit of mutual cooperation by interacting with other TFTs more frequently than with other ALDI players. Now, initially the numbers would increase, would fluctuate a lot, but you need to reach a critical threshold of TFT players for ALDI to prevent ALDI from exploiting TFT, right? So if that threshold is not reached, then it is not going to be possible for TFT to take over the population, because the ALDIs will keep exploiting the TFT players whenever they interact with them. And that is why it is harder to reach that threshold when the population size is large. Okay, and so that's why you see that there is an upper bound here in the strong selection case, where the payoff difference matters a lot because the selection strength is strong. So the ones that are having a higher payoff are more likely to be selected for reproduction, and this makes it difficult for TFT to cross that certain threshold that is necessary for getting the benefit of mutual cooperation from interacting with one another and taking over the population eventually. Okay. Okay. So so this is as far as the technical details of these models are concerned. So the key concepts that we explored were fixation probabilities in finite populations, both in the case of neutral evolution, which is important because it provides us with a benchmark for deciding whether for finite populations and frequency dependent fitness a mutant can invade. We looked at fixation probabilities when there is selection between two types, because the fitness of the two types are different but constant. We looked at a situation where the fitness was frequency dependent, so selection, evolution with selection in the case of a game with strategic interactions, and we were able to extend the results for fixation probability calculation to this case and determine the modified condition for ESS in finite populations. Okay. So now I'm going to shift gears a little bit and go from the well-mixed population model that we have been restricted to so far to structured populations. And that is useful because we can show, or others have shown, that it is easier to sustain cooperation in structured populations than in well-mixed populations, right? So if you play this game with just cooperators and defectors, even for finite populations, if you don't have TFT, cooperators will never be able to invade, no matter how you tweak the population size. But that changes when you go to finite populations which are structured. Okay. Yeah. So W is the same W that I was using as the selection strength.
There's another W in the temperature.
Yeah, it's the same thing. It's the same thing.
Okay, then,
this result is not with that temperature W. So this is with the Moran process.
So you usually in this settings talk about TFT.
Yeah.
But what about other strategies like Pavlov or something similar analysis can be done, or they are not really interesting in this kind of analysis?
It's possible to do so for some strategy. You can write down the payoff matrix for any strategy,
And then work out.
any reactive strategy, or any memory one strategy interacting with any other memory one strategy or reactive strategy, and then come to the conclusions. But the fixation probability calculation is not always easy to do.
So when you go to the network setting,
Yeah.
is this kind of an analysis helpful there to figure out something
Yes.
happening locally?
It is helpful in terms of setting benchmarks to determine whether we have an advantage in a network setting or not. Okay, so then, so for structured populations, it's difficult to get analytical results, although there are some exceptions which I'll briefly mention. And you have to stick to what are called agent-based simulations. So I'm sure a lot of you have, all of you have heard this term. Now, yesterday there was a talk which talked about agent-based simulations in finance. So agent-based simulations are ones where you have different agents who are interacting with one another, and each agent is functioning based on certain rules that have been imposed on them. The interaction rules are completely determined, and then we simulate this population of agents when they interact with one another, and see what happens to the population, how does it evolve, right? And the whole point of doing these agent-based simulations is that it gives you insight in situations which are not possible to handle analytically, right? As in the case of complex networks and even other kind of structured populations like a lattice and so on. So what you have to do for these kinds of simulations are essentially 3 steps. So you must specify your initial configuration, which specify the initial distribution of different strategies in the population. You must, of course, fix the type of network that you are working with. It can be a spatial lattice, it can be a random network, it can be a random regular network, it can be a scale-free network. You have all probably heard these terms by now. So once you fix your network topology, you distribute the agents on the different nodes of the network, and initially maybe at random, and then there's an interaction phase which after which you can calculate the payoffs. So every agent then interacts with every other agent which it is connected with. So unlike an unstructured well-mixed population, an agent cannot interact with every member of the population. It can interact only with members it is connected with, right? So every interaction leads to a payoff for the focal agent that you have picked, and you calculate the payoff from all interactions, sum up the payoff, and do that repeatedly for every single agent on every single node in the network, right? And then you go to the strategy update stage, where you update the strategies of the agents using specific deterministic or stochastic update rules, which can be, there can be many different such rules. It's up to you to choose the kind of rules. We'll talk about a few of them. So this is the basic idea. So we want to implement a simulation of a population of cooperators and defectors who are interacting with each other, but who are initially distributed on a 2D spatial lattice. And the reason I started off by restricting the discussion to a 2D spatial lattice is because it allows you to visualize what is happening pretty nicely, get intuitions by looking at the dynamics. I'll show you in a moment how that looks like, and see what are the conditions under which cooperators can avoid being invaded by defectors and so on. Okay. So here's a snapshot of the lattice with a certain distribution of cooperators and defectors, and so suppose I focus on this central site. You can see that it is surrounded by 4 defectors and 4 cooperators. When it interacts with, so this model has been, this payoff matrix has been simplified a bit. So whenever it interacts with 4 defectors, it gets a payoff equal to D. When it interacts with 4 cooperators, it gets a payoff, each time it gets an payoff equal to C. So the total payoff from interacting with 4 cooperators is 4C. So 4C plus 4D becomes the total payoff to this focal player as a result of its interaction with all its neighbors, right? So in this situation, which are the connected neighbors? The connected, I can define my neighborhood, and in this case the neighborhood is one where all the immediate neighbors, nearest neighbors are connected neighbors, including the diagonal ones. Okay. And similarly, you repeat this process for every site, and then once you get the payoff for every single lattice site in the population, you have to go to the update stage where you are updating whether choosing a lattice site and deciding whether it's going to remain as a defector or going to flip to a cooperator and so on. So one update rule that is shown here is deterministic. So I look at all my neighboring sites and decide to change the strategy to one which has the highest payoff among all my neighbors. Okay. So if all my neighbors, if among all my neighbors this site has a larger payoff, then this becomes a cooperator. Okay. So this is how you proceed, and this is just a simplification of this model where A has been set to 1, B has been set to 0, B sees the benefit of cooperation without paying the cost, so that has been set equal to B. B stands for benefit, and D is a very small quantity which is effectively set to 0. So this reduces to these quantities, right? So C becomes 4B and so on. Okay. So there's an alternative method of strategy update. Everything else I mentioned holds true for this case except for the strategy update, where now you have a stochastic strategy update. So you decide whether this site flips to a cooperator or not in a way that is not deterministic but stochastic. So what is the rule that is followed in the simulation that I will show? The rule that is followed is you calculate the fitness of all the neighboring cooperators and all the neighboring defectors, sum them up together, and the fitness of this central site, if it's a cooperator, will be given by the so the fractional fitness of this one would be determined by the fitness of all the cooperators divided by the fitness of all the cooperators and defectors, right? So this becomes the fractional fitness of cooperators if this is a cooperator. Similarly, you can calculate the fractional fitness of a defector if this is a defector, and then you choose a random number. and you choose a random number, and based on these rules, which I'm not going to go into the details, you decide whether it flips or not. Okay. So now let's go to the movie. So this is an initial configuration where the initial lattice is such that there are 50% cooperators and 50% defectors, which are randomly distributed across the lattice. The altruistic probability and the selfish probability just correspond to the initial fraction of cooperators and defectors. And there's a cost of altruism and the benefit of altruism. So these numbers you can change. So I've fixed them at certain value for a reason. So let's run the simulation and see what happens. Okay. So this gives you the frequency of this is actually the number of the altruists and selfish agents in the population. And you can see that even though initially it was 50-50, the altruists start taking over and eventually take over. So why is that? Why is it? Is because I had set a very high benefit for altruism, right? If I change the benefit a little bit, repeat the setup, even if you start off with a initial configuration where there are 50-50, it's hard for nice people to spread in the population, right?
Here the update is based on the instantaneous payoff rate, not the cumulative payoff from the previous.
It is based on not over number of rounds. So it is based on cumulative payoff in the sense that it's calculating its payoff with all its neighbors.
Not over time.
Not over time, yeah. So okay, so let's run this simulation a little bit slowly and see what happens. And there's a reason why I want to do that, right? Okay, so let's stop here. So you see that you can already see at this stage that the number of selfish agents is larger than the number of altruists, right? But the other thing that you should notice are these islands or clusters of altruists which appear. So they are putting up a valiant fight against these selfish agents, trying to prevent the selfish agents from encroaching and taking over, right? To what extent are they able to do that? Are they successful in doing that? Well, when altruists come together, they can get the benefit of mutual cooperation, right? And so if you look at this cluster, for instance, there are many altruists who are interacting with other altruists in the population, and so each of them gets the benefit of mutual cooperation, and that's how they are able to increase their payoff. But at the edges, the altruists which lie at the edges are interacting with defectors, right? And they are being exploited by the defectors. So in the next time step, whether this altruist will be taken over by one of the defector neighbors or not depends on what sort of neighborhood it is lying in. So this altruist is not in a good state because it has 1, 2, 3 altruist neighbors, but all the others are defectors. So it's going to end up with a smaller payoff, and it is quite likely that it's going to be taken over by a selfish agent in the next step, right? And so then the boundary of this shrinks, right? So whether a cluster of cooperators will grow or not depends on the cost to benefit ratio that comes into play at the boundary of these clusters, and to what extent they are able to evade the onslaught of defectors is determined by this cost to benefit ratio at the boundaries. That is why when I had increased the benefit from altruism initially to a large value, 0.71, the clusters were able to grow. But in this case, the clusters are shrinking. And if you continue the simulation, it'll eventually end up in a state where there are only selfish agents in the population. Okay. So I hope this gives you a sense of how important the underlying population structure is in determining whether a strategy can take over a population or not. So not just the population structure, it of course depends on the benefit to cost ratio of altruistic behavior. So all these factors determine whether an altruist can survive. Okay. So any questions so far? Okay. So one nice thing about this model is that it can lead to some extraordinarily beautiful patterns. And you can see this Persian carpet-like pattern which emerges for certain parameter values as you run this simulation. So this shows you for different benefits of altruistic acts, how the population structure changes, and here as B increases, so B, if you recall, was this redefined parameter. So B is the benefit that a selfish agent gets when it interacts with a cooperator, and the cooperator gets nothing, right? So as you increase B, it becomes less and less likely for cooperators to be sustained in the population, though you see these islands, but they will eventually vanish as I showed in the simulation. But for a certain value, if you run the simulation over a long enough time, you get these kind of patterns and that emerge. Okay. Okay, so I want to extend these results that are obtained for a very regular spatial lattice to see what happens when you go to more complex network structures, right? And in order to do that, we need to be able to calculate fixation probabilities on such network structured graphs. And so this is an example of a network structure. So what I'll do in the next few slides is to just give you a sense of how network structure can affect fixation probabilities, how it can change fixation probabilities from what we saw in the well-mixed population scenario, and when it doesn't change fixation probability compared to what we saw in the well-mixed population scenario. And eventually, I want to give you a sense of these results, because then I'll show you an example where you have a complex network structured population, and then it's possible to show whether cooperators can invade or not. So, so let's look at this a little bit. So next few slides will focus on pointing out how fixation probabilities are calculated on certain simple structures and so on. So here's the basic idea. Can structured populations increase fixation probabilities of advantageous mutants? So these are the main questions that I want to address, or that are usually discussed in the literature. Can certain structured populations eliminate the effect of selection altogether, right? So in a well-mixed population, if you have a fitter individual and it has a certain probability of getting fixed in the population, can you go to a network structured population and show that the fixation probability becomes the same as the there's no advantage to be gained from being a fitter variant, and the fixation probability is the same as that of a neutral mutant. So you're all familiar with, so the unstructured population limit can be obtained by making sure that every node is connected to every other node in the population. Okay. So how do we start by doing that? So we have to first calculate, first decide how a node is picked for reproduction and which node it is going to replace in this network, right? It is going to be able to replace only those nodes which, suppose this is picked for reproduction, so it is only going to be able to replace those nodes with which it is connected. And the directed arrows mean that it can replace this node, it can replace this node, but not this node, because there's no arrow going from this to this one. Okay. So one can write down a stochastic matrix that determines the probability of replacing the jth node by the ith node. And if this element wij equal to 0, then that means that there is no directed edge from I to j. So offspring of I cannot replace j. And the sum of the rows of this stochastic matrix has to add up to 1, because if you pick an ith member for reproduction, it has to replace somebody or the other in this population, either itself or some other node it is connected with, right? So here's a couple of examples where you have a certain directed structure. So I have this is called a directed cycle, and this means that this node can replace this one, but it cannot replace this one. So that's why it's directed. It can only replace the node that follows it, but not the node that precedes it. And so what would be the stochastic matrix that one can write down? So you can number each of these rows and columns by the node number. So 1, 2, 3, 4 like this, 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, and you go down. So one can replace 2, right? And it is the only node it can replace. So that's why it replaces 2 with a probability 1, and all the other terms are 0. 2 can replace 3, right? And so on. So this is the stochastic matrix. For an undirected cycle, or just a cycle as it is called, undirected in the sense that this node can replace both the node that follows it as well as the node that precedes it. And in this case, so node 1 can replace 2, but it can also be replaced by node n, right? So node n is the it can also replace node n, right? So that's why there are equal possibilities of replacements of these two nodes by the first node, and so that's why I've put half here. Similarly, for this one, it can replace 1, this one preceding it, and it can replace 3 with equal probabilities, and so on. So how do I calculate the fixation probability of a mutant in such a graph? So suppose you start off with a cluster of m B-type players. B-type are the blues. And suppose the fitness of, just to make sure I'm getting, yeah. Suppose the fitness of a B-type is larger, is characterized by R, and the fitness of A-type is 1. Okay. So I can use the Moran process to calculate the transition probabilities. Suppose I start from a state where there's a certain cluster of B nodes, right? And this cluster size is m. So I want to calculate how I can go from m to m minus 1, and I want to calculate how I can go from m to m plus 1. So this B can be replaced by A, and suppose I'm looking at a directed cycle. So how can a cluster of B decrease in size? It can decrease in size. First of all, I hope you appreciate that there cannot be disconnected clusters in this graph. Because of the nature of the underlying population structure. So a B can decrease in size only if this A replaces this B, right? This is the only possibility by which the number of B players can decrease from m to m minus 1, right? So B has to be picked for death, and a specific A has to be picked for reproduction. So what is the probability of picking B for death? Well, it's R, it's 1 by n minus m. And what's the probability of picking, sorry, so not n minus m, so just I'm picking this B for death, right? So the probability of picking this for death is 1 by n. And what is the probability of picking A for reproduction? A has a fitness equal to 1, and the total fitness is 1 into n minus m plus R times m, right? So keep in mind that any A cannot replace B. So this is not going to be n minus m, right? So it's going to be 1, because this is the specific A that I have to choose to replace this B. And similarly, the number can increase by 1 if I pick this for reproduction and this for death. So picking this for death is 1 by n, and picking this for reproduction is R by Rm plus n minus m into 1. Okay. And so I can calculate this ratio p m m minus 1 and it turns out to be 1 by r. And because it turns out to be 1 by r, I can just plug it in back into this expression and show that the fixation probability is the same as what you would expect in a well mixed population. So it just depends on the ratio of these transition probabilities.
The van process, I cannot take any interior point in the B cluster, right, for changing. That's not possible.
No, it's because of the structure.
Okay.
It's because because if I take any interior point, if I pick this point,
Okay, that's not possible.
then the number of bees will not change. Okay. Okay. So similarly, you can calculate the fixation probability for this as well, and it turns out to be the same. So here's an example where you have two different population structures, and both give the same fixation probability for a mutant with a fitness which is different from a wild type, and that fixation probability is same as the one that you obtained in a well mixed case. But here's a counter example which shows how a structure can affect fixation probability rather dramatically. So suppose I have a line graph, right? So what is the probability that a single blue mutant which appears will take over the entire population? Now you can see that if the blue mutant appears anywhere other than this first position, it will not be able to take over the population, right? So if it appears here, it cannot replace this one, so this remains, it cannot take over. So only if it appears here will it be able to take over the population. And what is the probability with which a blue mutant will appear here? It is given by just 1 by n, because this is, you can pick this site with a probability 1 by n, because there are n sites, right? And so the fixation probability of this blue mutant is 1 by n, which is the same as a neutral fixation probability. So it doesn't matter whether the blue mutant is a fitter variant compared to the red wild type. The fitness has no effect whatsoever. And so this is an example of an underlying network structure which reduces your fixation probability compared to what you would expect in the mixed population scenario. Okay. So there are other examples, and so the key point here is you can classify different network structures based on whether the fixation probability of a mutant you obtain on such a structure is larger than what you would expect in a well structured population, or smaller than what you would expect in a well structured population. And if the fixation probability happens to be larger than what you would expect in a well structured population, then that kind of structure is called an amplifier of selection, because it favors the fixation of the mutant in such a structure compared to a well mixed population, and so on. So the other case, it's a suppressor of selection if the fixation probability is less than what you expect in a well mixed population. And the strongest possible suppressor of selection is one where the fixation probability differs, doesn't differ from what you would expect by chance, which is 1 by n. So these graphs are the strongest possible suppressors of selection where fitness difference doesn't matter at all. Okay, so now let's go to the final part. I think I'm on time. So now you have a sense that an underlying network structure can affect fixation probabilities. It can affect the ESS condition. of course, any finite population would affect the ESS condition, but an underlying network structure can additionally affect fixation probabilities. And so you can ask the question whether if I put a distribution of cooperators and defectors on a network structured population, which is more complicated than a regular lattice that I showed, can I obtain the condition for fixation of cooperators? So can cooperators prevail in network structured populations despite the fact that we know that they cannot survive in well mixed populations? Yeah.
Over there, when you assume that the probability of reaching each node is equal,
Mhm.
1 by n, that doesn't seem justified because some nodes are connected to many more nodes, and some nodes are just connected to one other node. And the idea of saying that each node is equally probabilistic is not something that is.
No, so each node is equally, so it is in this sense. So if you want to change the probability of one node influencing another node, so you change these probabilities. So instead of saying that this can replace this with a probability half as well as this with a probability half, you can say that this can replace this with a probability of 3/4 and this with a probability 1/4. Okay. So you can change those weights in this stochastic transition matrix as you wish. Does that answer your question? Yeah.
It's 1 by n for me to be the first node. Like, where does that happen?
Oh, because you have to pick the first node, right? So
when we pick the first node, so my question is, how do you decide the probability of picking it? Is it just the number of nodes divided by total number of nodes, or does it include the distribution of edges, and the degree of that node divided by total degree?
no. So in this case, it is. Yeah, okay, I see what you're saying. So it depends on, here the first node is well defined, right? There are graphs, which is probably what you have in mind, where it's hard to figure out which the first node is, right? And so in this case, the first node is well defined because you know that if you pick anything else other than this node, because of the directed nature of this graph, linear graph, this node cannot be replaced by any of the subsequent nodes. So, and so the mutant, when it appears, has to appear at this site, and it has to appear, and it will appear at this site with a probability of 1 by n.
Like an arbitrary graph, I choose
Yeah.
a certain node.
Yeah.
I want to come up with the probability of picking that. Would you just say that it's 1 divided?
It's 1 by n. Yes, it is 1 by n.
Or it should be the degree of that node divided by the
No.
average of total.
No, so the degree matters only when it comes to replacement, right? But here I am saying when does a mutant arise? Where does a mutant arise? Mutant suddenly appears at some point.
Right, so it's saying that it has equal probability of arising at all nodes. So, okay, it depends on the system that you.
Yeah, it depends on the system. So in this case, it has to appear at this node. Otherwise, it will not be able to take over. Yeah. Okay, so this is the question that was addressed in this paper by, okay, so suppose reference is missing. Oh, here it is. In this paper by Otsuki et al., who tried to calculate the fixation probability of cooperators in graph structured populations and obtained a remarkably simple expression for the condition required for cooperators to spread in such graph structured populations. And so what they found, that depending on the type of evolution process, and they use the Moran process, but there are some subtleties. So in network structured populations, if you whether you have a birth death or a death birth process can make a difference. So for a particular type of updating. So you have to pick an individual for death, and then the connected members of that individual that you have picked for death compete with that spot for that spot. And the other alternative is birth death. So one individual is picked for reproduction, and then it replaces one of its neighbors chosen at random. So there are subtleties between birth death and death birth. They don't always give the same result. So these two methods of updating are different. But what they found is that for death birth process, the fixation probability of cooperators to be larger than defectors, larger than what is expected by chance and larger than the fixation probability of defectors, is given by the simple rule: the benefit of cost ratio must be larger than the size, the degree of the network. So they had to, for their analytical calculations, which is extremely complicated, I'm not going to go into that, they had to deal with some special kind of networks called a Cayley tree or a Bethel lattice. So these networks have a property that there are no loops. So you cannot start from a node and trace a path back to the same node again. So these are ever expanding branches, and so there are no closed loops in such networks. And for that, they were able to show that the fixation probability depends on this benefit to cost ratio being larger than the degree of the network. And this is the graph, kind of graph that gives, so the results are good, the analytical results are good for for non-regular, for regular graphs. So so this is a random regular graph. So you get these arrows are the values of the benefit to cost ratio at which as predicted by the theory, and these dots are the simulation results. So the key result is that the benefit to cost ratio is larger than the population size. Sorry, the degree of the network. Okay, so I think I'll, this is the final slide, which is a bit of about what you can do in the future. So if you are interested, if you have developed an interest in this area. And this is a very biased sample based on what my interests are and what I know about. So, so I apologize for. So the take-home message that I want to leave you with is this evolution of cooperation is a very rich phenomena, and there's scope for a lot of interesting work, and one particular direction that I find quite exciting has to do with this update process that I told you about. So when I started off my lecture, I showed a slide saying that behavior is a very complex phenomena. It depends on many different factors, and all of us take into account many different factors when we are taking a decision, and we also learn based on our past experience. And so far in all the discussion that has gone on over the last week, the aspect of learning has been totally left out of the picture. But learning how to change our strategies is a very important aspect that needs to be incorporated in these evolutionary game theoretic models which try to explain evolution of cooperation. And there are many different kind of learning mechanisms or learning rules that you can fiddle with. How do we learn from our neighbors in the social network in which we are embedded in? How do we incorporate that kind of learning into our decision making? how do we learn from past experience, which is based on which can be described by Bayesian learning. What about reinforcement learning? So what if we find that certain actions lead to large payoffs, and that reinforces our beliefs in those actions, so we tend to carry out those actions with higher frequency and larger probability. So I don't know if Wolfram Barfus's talk discussed these issues or not, but this is an aspect that is being increasingly discussed in the literature. And what about heterogeneous learning strategies? I mean, all of us have different learning mechanisms. We give emphasis on different aspects of human behavior and decision making. So in a population, all the agents do not have to have the same learning strategies. They can have different learning strategies. So what if we incorporate heterogeneous learning strategies in the population to see how evolution, cooperation is affected? So far you have talked about, you have heard about games, but you have heard about just one game. But we often indulge in or engage in multiple strategic interactions with multiple different neighbors in the population. So what if we look at multiple games that are going on, and how by looking at these kinds of games, each yielding a different kind of payoff, can we better understand evolution of cooperation. And finally, one assumption that has been there throughout all these lectures is that the payoff matrix is constant. So you start with a payoff matrix and that remains fixed. But in a lot of the strategic interactions that we are involved in, the environment changes, as a result of which the payoff matrix changes. So the strategic nature of the interactions changes. So what if there are switches between different types of strategic interactions? So these form a class of games called stochastic games, and to what extent are those helpful in understanding evolution of cooperation and other phenomena on other social phenomena on lattice. So I hope you have got some flavor of this topic, and I hope at least some of you are a bit excited about exploring more about it. Okay, thank you.